Simultaneous systems of differential equations continued. Now, we will look at the direct method. So a linear system of n autonomous differential equations is expressed in matrix form as y dot is equal to ay plus b, where A is an n by n matrix of constant coefficients, B is a vector of n constant terms, y is a vector of n variables, and y dot is a vector of n derivatives. So all the vector terms are in bold. And when we have n equal to two linear autonomous differential equations, A is equal to A11, A12, A21, A22. So this is the coefficient matrix. And the vector of terms is B, bold B, is equal to B1, B2. As always, the solution to the complete system of equations is obtained by adding together the homogeneous and the particular solutions. Now, the complete system in homogeneous form is y dot is equal to ay, right? So homogeneous form, we get rid of b, we replace it with 0. And this is the homogeneous form, y dot is equal to ay. Now begin by guessing, quote unquote, that the homogeneous solutions are of the form y is equal to k e to the power rt, where k is an n-dimensional vector of constants and r is a scalar. To see if this guess is correct, check that the guessed solution and its first derivative satisfy the differential equation system. The derivative of the proposed solution is y dot is equal to r k e to the power rt, right? So when we differentiate both sides, this is what we get. Now plug y and y dot into y dot is equal to ay. So y dot is equal to this thing on the left-hand side. We have a times y, and y is equal to k e to the power rt, so we have it over here. Simplify, right? So e to the power rt, e to the power rt will cancel. You could take rk to the right-hand side, you'll have ak minus rk. You can take k common, and inside brackets, you will get a minus ri. When we multiply r by the identity matrix, it remains the same, right? So where I is the identity matrix and 0 is the 0 vector. The values of r which solve this equation are the values of r which make our guess solution correct. We would get a non-trivial solution if and only if the determinant of a minus ri is equal to 0. Now, the determinant of ai equal to 0 is the characteristic equation of matrix A, and the solutions, Ri, are called the characteristic roots or eigenvalues of A, and a non-zero vector K1, which is a solution of A minus Ri times K is equal to 0, for a particular eigenvalue R1, is the eigenvector of the matrix A, corresponding to R1. All of this is familiar from our study of further topics in linear algebra. In the case of n equal to 2, we have the determinant a11 minus r, a12, a21, a22 minus r. The determinant is equal to 0, which implies that r squared minus a11 plus a22 times r plus a11, a22 minus a12 times a21 is equal to 0. Which is the same characteristic equation we obtained from the substitution method. So please check it. You will see that it is the same equation. Now notice that A11 plus A22 is just the trace of A. So the trace of a matrix is the sum of the diagonal terms. So the coefficient matrix A11, A12, A21, A22, when you add A11 and A22, the diagonal terms, you get the trace. And A11, A22 minus A12, A21 is just the determinant of the matrix A. So we can write the characteristic equation as r squared minus trace of A times r plus the determinant of r is equal to 0. The roots of the characteristic equation, R1, R2, are the trace of A by 2 plus minus half the square root of trace of A squared minus 4 times the determinant of A. Now, this expression allows us to quickly calculate the characteristic roots directly from the coefficient matrix. So if you have the coefficient matrix, Use this formula and you'll get the characteristic roots directly. Now, if there are n equations, there will be n characteristic roots and n solutions to the system of differential equations. General solution to the homogeneous form is a linear combination of n distinct solutions. Now, if y1, y2 up to yn are linearly independent solutions of a homogeneous system, y dot is equal to ay, then the general solution of the system is the linear combination y of t is equal to c1 y1 plus c2 y2 plus all the way up to cn yn for a unique choice of the constants, right? So c1, c2, and cn will be unique constants. Now, please study example 24.8 on page 798 of Hoy, the third edition, right? Please study the example carefully. Now, let us solve the following system of homogeneous, right, differential equations. We encountered them earlier. So we have y1 dot is equal to y1 minus 3y2, and y2 dot is equal to 1 by 4y1 plus 3y2. What is the required coefficient matrix? It is 1 minus 3, 1 by 4 plus 3. The characteristic equation a minus r equal to 0, or 1 minus r minus 3, 1 by 4, 3 minus r is equal to 0, which gives us r squared minus 4r plus 15 by 4 is equal to 0, with roots r1 equal to 3 by 2 and r2 is equal to 5 by 2, same as before. So in the other example, you got the same characteristic equation and the same roots. Now first, for r1 equal to 3 by 2, we replace r with 3 by 2 and we obtain this expression, this equation. Set k1 equal to 1, right? Actually, k1 could be set as any convenient value because k2 is simply a multiple of k1. So you can set k1 to be any value. So we set k1 equal to 1, and that gives us k2 equal to minus 1 by 6. So the first set of solutions is y1 equal to 1 minus 1 by 6 times e to the power 3t by 2, okay? Or e to the power 3t by 2 minus 1 by 6 e to the power 3t by 2. Repeat the procedure for r2, the second root, and r2 is equal to 5 by 2. Use k1 equal to 1 again and obtain y2 is equal to 1 minus half e to the times e to the power 5t by 2. Now, since the two solutions are linearly independent, the general solution is the sum. So y of t is equal to c1 times this thing, plus y2 is equal to c2 times this thing. Evaluate the products, right? Remove the brackets and confirm that it is indeed the same solution that we got before. Now, in order to obtain the particular solutions, once again, the easiest way is to simply use the steady state condition y dot equal to 0 in the original differential equations. Okay, the original differential equations. Obtain y bar, right, and then add them to the homogeneous solutions. However, more formally, if we have a y bar plus b is equal to 0, then y bar would be equal to minus a inverse b. There's no need to calculate y bar in this fashion. The easier way is to plug in y1 dot equal to 0 and y2 dot equal to 0 in the original differential equations, and then solve them simultaneously for y1 and y2. Carefully study example 24.10 on page 800 of Hoy, third edition, to see how the direct method is applied to a system of differential equations with complex roots. Study the example very carefully. Now, just as we have seen that it is possible to convert a system of two separate linear first order differential equations into one second order differential equation, the opposite is also true. We can transform any second order differential equation into a system of two first order equations. Now consider the differential equation y double dot minus a1y dot minus a2y is equal to b. Define a new variable as x equal to y dot. This means that x dot is equal to y double dot when we differentiate both sides. Substitute this, right, and x equal to y dot into the second order equation. So replace y double dot with x dot and replace y dot with x, right? And we will now have the following system of two separate first order linear differential equations. X dot equal to a1x plus a2y plus b, and y dot is equal to x. Now compare this with y1 dot is equal to a11 y1 plus a12 y2 plus b1, and y2 dot is equal to a21 y1 plus a22 y2 plus b2. Notice that x is equal to y1, y is equal to y2, a1 is equal to a11, a2 is equal to a12, a21 is equal to 1, and a22 equal to 0. Now we can solve for y of t and x of t in the usual manner using the direct method. You know, you have the elements of the coefficient matrix, and then the characteristic equation will give you the roots, and you can solve for both equations. But of course, in this particular case, we would only be interested in the solution for y of t. And of course, you could also use the substitution method to solve this pair of equations, and you should go ahead and do it. Now recall the example of a current value problem, which we saw in a previous lecture. Here we need to maximize between 0 and t e to the power negative rho t times ax minus bx squared minus cy squared, subject to these constraints. X dot is equal to y minus alpha x, and x of 0 is equal to x naught. We set up the current valued Hamiltonian. We obtain the first order conditions, and we end up with this pair of differential equations, and we need to solve them simultaneously. We stated the solutions previously, but now we are going to see how to obtain the values of Ri, mu bar, and x bar from the differential equations. So this is the pair of differential equations that needs to be solved simultaneously. First, express them in homogeneous form. So to do that, get rid of the a, replace it with 0. And the equation for x dot is already homogeneous. And write this pair of differential equations in matrix form. So you have mu dot x dot is equal to alpha plus rho 2b 1 by 2c minus alpha times mu and x, right? So this is the coefficient matrix. Now the trace of this coefficient matrix is alpha plus rho minus alpha, which is just equal to rho. And the determinant is minus alpha squared minus rho alpha minus b by c. Please calculate it yourself. Which gives us the roots R1 and R2 using the formula trace of a plus minus square root of trace of a squared minus 4 times the determinant by 2. And that gives us rho plus minus square root of rho squared minus 4 into the determinant of a minus alpha squared minus rho alpha minus b by c divided by 2. Now, in order to get mu bar and x bar, use the steady state conditions mu dot equal to 0 and x dot equal to 0 in the original differential equations, not the homogeneous form, always remember, and solve the resulting pair of equations simultaneously. Or you could use the formulae, which is in slide 8 of the differential equations chapter, differential equations 1 slides. You should obtain x bar equal to this thing, a by this thing, and mu bar is equal to alpha ac by this thing. And this means that our solutions are mu of t equal to c1 e to the power r1t plus c2 e to the power r2t plus mu bar, and x of t is equal to r1 minus rho minus alpha by 2b times c1 e to the power r1t plus r2 minus rho minus alpha by 2b c2 e to the power r2t plus x bar, right? So x bar and mu bar are this, and R1 and R2 are this, right? R1 is rho plus this thing, and R2 is rho minus this thing. Now the value of capital T is not given, making this a free endpoint problem. So utilize the boundary conditions x of 0 is equal to x naught, and mu of capital T is equal to 0 because T is finite. And then you can solve for C1 and C2, and you should do it.